Hello, hello. Hello. Okay. Wait, no. Wait. Hello, Amanda. Hello, Isabella. I mean, good afternoon, Isabella. Awesome. Hello, Rachel. Hello. That's awesome. Hello. I'm still. Oh, someone else is here. Sorry. Oh, and actually, hello, Melissa. I'm still here. Wait, sorry. Hello, Ingrid. Hello. Um, hello, Ingrid. That's awesome. Hello. 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 Sorry. Hello, Ardell. Hello, Ardell. Hello, Ardell. Hello, Amanda, Isabella, Rachel, Melissa, Ingrid. Oh, hello, Kaylee. Hello, Aaliyah. Hello, Tania. Hello. All right, we're gonna get started. Okay. We are recording. Okay. Who else? Oh, hello, Miles. Hello, Crystal. Hello, Kaylee. I said, okay, I think, Viola. Viola, hello. Okay, I think that's everybody. Okay, hello, hello. Hello. So we're going to get rolling in a second. Da, 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 da. Today we're going to cover a lot. I think if my experience in the other class is any indication, I think we're going to get through a lot. And I think like the goal of today, the goal is that by the time we're done today, you should really, you'll see that homework 3, if you haven't done it, which is most people have not, you'll see that homework 3 is very doable by the end of today. It might already seem doable, or it might seem totally undoable, but it should seem doable, very doable by the end of today, which also means that tacitly, in retrospect, you'll see that methods number 2 is doable. Now, today, mostly we're going to be going over number 2. We're going to start at the beginning of number 2, of homework number 2. Okay, you're going to see some repetition and some exercisey, practicey stuff, and you're going to see before we're a third of the way through homework 2. Hopefully you will see that homework 3 is more practice of kind of the same. Like in some ways, homework 3 is easier than homework 2. In some ways, it's certainly shorter. Saying all this, so what we're really going to do in a second when we start is we're going to be walking through homework 2 because it's like about time. Now, the truth is that as of if you handed in something in the past few hours or yesterday, then I haven't gotten to it yet. But as of like Sunday night or Monday, it is actually true that a ton of people in this group still had yet to turn in homework 2. And I had sent mixed signals about that. And it's still true that it is, to be as clear as possible, if you were to hand in homework 2 now or next week, I would still not mark it as late. Like I want you to turn it in. It's like really important actually that you, like it is now time to do homework 2. As I think wait, sorry, I'm trying to let someone in. It's not working. Hold on, sorry. I know someone's trying to get in. Why is it not working? Wait, pardon me for a second. Okay. Like again, I think I'm sending mixed signals. I'm telling you, it is definitely time to do homework 2. It's time to do homework 2 if you haven't done it yet. If you just did it recently and haven't gotten it back yet, that's on me, and I will get back to you soon. Apologies. If at any time you didn't do it because you looked at it and looked crazy intimidating, that problem should be solved by the end of today. And no harm, no foul. So let me say this again more clearly. Like I think a lot of people still haven't done homework 2. It is now time to do it. Today we're going to start going over it. We're literally going to go over like the first set of questions. If you already did them and you got credit, then you know who you are and great. And I'm sorry to bore you today or whatever. But okay, yeah, no, cool. No, there's no, I want to be very super clear, right? There's no penalty, there's no criticism, there's no shame here. To be everybody, we're gonna, but it's time for us to start going over homework 2. Hopefully when we go over the first couple on homework 2, it's going to help a lot of you, and you are welcome to, you're not cheating. I want you, you're welcome to like copy down your notes from what we do today and like use those as your way of solving the first couple of questions. Like it's not copying, it's like what we're here for. And if nothing else, you're showing me that you take good notes, right? But then hopefully it'll make it easier for you to do question 3, question 4, old school. So, but I do want the homework 2s. They're definitely not late. They won't be marked late, but I do want them also, once you get in a groove in them and see after today that they're not as bad as you might think, or at least not the derivative parts. Like homework 2 is long. That's the other thing. I know it's long and there's other parts. We'll still not derivative parts. You almost could like, if you get bored today, any of you who has done homework 2, by the way, just turn your attention just while we're talking today, look at homework 3 and you'll see it's directly what we're doing today. Okay. Not to overtalk it, but and finally, then I won't be posting homework 4 for a little bit. Like we'll all catch up with each other. But that's where. Thank you so much. I really thank you. I really appreciate it. Thank you. That's where we are. Will be homework 3 for a little while. Like if you've done it, then you're good for. Oh, I guess we had talked about exams too. Okay, we have to get to that. Yeah, but interesting. But all right. But again, I'm going to start going over homework 2 now. It is not meant to mess with anybody who hasn't done it. It also doesn't get you off the hook. You still have to do it, is the point. But it's also not meant to bore anybody who has done it. But here we, yeah. Oh, well, yeah. Okay. So, and if there's any questions or anything, obviously put them in the chat. Let me just get rolling here, get the thing up. Right. Okay. So I think this is where we are today, right? This is, yeah, I'm just checking the chat to make sure. Okay. Okay, but to summarize, this is where I think we are right now. Oh, and we are going to take it. We're soon momentarily going to take out homework 2 and start walking through it. But first, a preview, like context. As far as I'm concerned, this is where we've gotten to as of the end of Monday. Like after all of our talking about homework 1, which never put it away, by the way. It's like everything in the class is sort of like based on homework 1. But with all of our talking and our Hooke's law, x's and f equals negative kx and f net equals ma, and so then negative kx equals ma, like all this talk, we finally got to a point of seeing a differential equation that had x's in it. And then we got a solution to that differential equation that had x's in it. And we said a bunch of things about those x's, and in fact, by the end of Monday, I called the things that we had said and we're trying to learn from homework 1, from talking about springs. Basically, the things that we learned, we put together in a way and ended up calling them finding number 1 last Monday. Like finding number 1 was something about x equals a cosine omega t and d2x over dt squared equals blah blah. Then we said by the end of Monday, we said finding number 2, which is what's written right here on the board. Okay, so like this is now like where I think we're at now. Finding number 2 is a summary of everything we did up till finding number 1, but magically, secretly, whatever, I changed the x's to z's now. Like, and why am I doing that? What's my point? I'm saying that once we feel like we really understand what's going on with a mass on a spring, once we as physicists, I'm not saying we're all there yet as a group, or that we need to be. But as we think more and more about looking at a spring, knowing the forces acting on it, and then being able to predict from knowing those forces, from knowing Hooke's law, that we predict, okay, if you want to be able to tell, if I want to be able to tell you where this mass is going to be at any given moment in its motion, if I want a position function for it, an equation of motion, like an x equals some function of t, then I do this math stuff to solve for Hooke's law, and I get an equation x equals, I get an x equation. Like again, this is finding 1. This is what we did Monday. I get an x equation like x equals x naught cosine omega t that tells me where this mass will be at any given moment, assuming that it's on a metal spring of stiffness k, right? Like that's what we have been learning for like weeks and weeks. And it does actually take weeks and weeks for us to be learning that. But that was all about x displacements given some actual mass on an actual coiled spring. We did all this math to figure that out. So then what we're saying now in finding 2, in finding what I called finding number 2 last Monday, what we're saying is, wait a second, if math figured out all that physics for us, the math is a tool. Like the math doesn't know about the physics. The math doesn't care where we got our numbers from, whether we got them in a lab or whatever. Sorry, oh, I just noticed that's weird. But the math doesn't care about the numbers or even what they mean or where we got them. It just knows the relationships between X and A and T. And in fact, the math doesn't care whether we call it X or Z or something else. So what we realize, now here's where we're going with this, and this is what I call finding number 2, and this is like the point right now is we can generalize our finding. We were particularly just looking at some mass on some spring with some specific numbers like 200 and 0.15 and 0.3. We can generalize and say, you know what, not only could it have been any mass on any spring, but actually it didn't have to be a spring. It didn't have to be a coil of metal, and it didn't even have to be displacements through linear space that we were measuring. As you saw in lab number 2, you can set up a system where what you're measuring is not linear positions, but angular positions, right? The pendulum lab number 2, and granted it was a simulation, but like we realized, wait a second, actually we can find systems, we can measure things other than linear distance. We can measure like angular distance, or we can measure any variable in the world we want. And if we really trust the math, then any quantity you can imagine, any dependent variable, I should say, well, yeah. Whoa, sorry, hold on. Whoa. It's Gus Johnson time. Okay, well, that's illegible. But what that's supposed to say is that Z stands for any measurable dependent variable that you can conceive of. Like anything you can measure in the world that does that fluctuates at all or does anything in time, anything you conceive of measuring. What we're saying is if we really believe the math that we did on Monday, then picture any variable at all. Could be linear position, could be angular position, could be temperature, homework 3, could be electrostatic field, the next chapter in this class, could be magnetostatic field, could be electromagnetic radiation, i.e. like any quantity that you could imagine measuring or taking a bunch of measurements, a bunch of data readings, like as time progresses, any measurement in any science class, in any forensics undertaking. If you have reason to believe, and sorry, there's all this scrawl here, but if you have reason to believe that that dependent variable Z can be described by a differential equation, this differential equation, or that if you have reason to believe that Z is describable by this differential equation, if you have reason to believe that Z, the quantity you're measuring, if its second time derivative is directly proportional to itself, then it is oscillating harmonically in time. Like, and I'm going to say that again because that is a lot. Like, I'm trying to just say in English what this is saying here mathematically, but this is, and it doesn't help that I have all this blue scroll. Actually, yeah, I'm going to add a picture. Okay. I mean, this really is like such a, it is the point that we're trying to do right now with all this math. And it is like a big point in physics. So I'm going to just try to make this as clear as I can. So I'm saying if d2z dt squared equals negative omega squared z, like that's our differential equation. If, so in English, if the second time derivative of some variable, like z just stands for some variable that you can measure, some dependent variable, some variable that you're measuring with respect to time, or like as time flows, right? If the second time derivative of this variable is directly proportional to the variable itself, right? That's what this math is trying to say. Like before I go any further, like the left-hand side says second time derivative. And the right-hand side, really, it looks like gobbledygook, but the right-hand side is really just saying, wait, even better, I'm sorry. Right? Whenever you see that negative omega squared, remember that whole package just means some constant. Yes, it happens to be a negative constant. Like by putting the negative, by writing it the way we are, we're ensuring that omega is some kind of positive number that's being squared. And then we're negating it with a negative sign to ensure that the constant is negative. So we are promising ourselves that the constant is negative. But the point is, it's just some constant. Like the number -1 is just some constant. So to what it means to be direct, if I ever say y is directly proportional to x, that doesn't mean y equals x. It means y equals some constant times x, right? It means y equals mx plus b, right? If y is, it means y is a linear function of x. So that's what we're saying here. We're saying if you know of some variable whose rate of change with respect to time is directly proportional to the variable itself. Like if you know that to be true of a certain variable, and we often, and the thing is, nature tells us all the time that this is true of many variables in nature. Like it comes up all the time that we get this information from nature. If we have that information, then, oops, sorry. Oh, sorry. Okay, the key thing that I'm trying to say right here, that we already said in finding one about x's, but now I'm trying to sort of emphasize that this is going to be true in all for any variable that you can conceive of throughout math or physics, the physical world. So we're changing it to z to emphasize this is just a general variable now. Like we don't have to have springs that are made of metal coil anymore. We don't have to have distances that are like on a meter stick. Anytime any variable z can be described by this differential equation, right? If the rate of change or the rate of change, sorry, if the time rate of change of the time rate of change of z is directly proportional to z, well, first of all, that means that the time rate of change of the time rate of change is equal to a constant times z, right? Remember, I probably should add that page. In fact, well, you might want to add in your notes. Remember to say what, yeah, I'm going to say it. By cracky, I'm going to say it because by cracky. Oops, sorry. Okay, just remember, and it's vocabulary, like if we say one thing is directly proportional to another, we don't mean they're equal. We mean that one thing is equal to a constant times the other. Like y is directly proportional to x means y equals mx plus b. And like b could be 0 or whatever. But it means like, and what does that mean? It means the slope is constant. It means that you like, again, I've said this in one of the class, just like, because everything in like, because it's the relation that everybody likes in the world and in science. We like direct proportionality. We like it so much that sometimes we get confused and think everything is direct proportionality, but it isn't. The main actual trick of a scientist is to try to find direct proportionality when we can. So remember, direct proportionality means, well, it means this. It means this. So y is directly proportional to x means y equals some constant times x. Call it m if you like. M in English is known as the proportionality constant, the constant of proportionality, right? Like whatever it is, they're still proportional, right? So what we're saying here, then, we're saying as long as the second time derivative of some variable is directly proportional to the variable, if it's equal to some constant times -1 times the variable, then we have this powerful inference that we can draw right away. We can say then, so get right, then that variable, whatever it is, that quantity that we're measuring, necessarily is oscillating. First of all, like if we right away, if we just know that it satisfies that differential equation, we know we have an oscillator. We might not see a spring, we might not see metal, we might not see a mass, but we know some value. Like it might be a temperature thing, like homework 3. It might be a temperature thing where we for some reason from data from curves or for something, or somehow we know that the temperature is satisfying this differential equation, like right at the top of homework 3. We can right away know the solution to that differential equation because we've already done it in math, and math doesn't care whether we're talking about temperature or springs. So we say right away, aha, if temperature is described by that differential equation, then temperature is oscillating in time. It's going up and down like a mass on a spring, and going up and down exactly like a mass on a spring. Like all of its values are doing the same thing. Like this is what we can say from here on in. Anytime we know that this differential equation describes something, we know right away that that thing is physically acting like a mass on a spring. It's going back and forth at a steady rate, a rate that is independent of how we set it up. Hence, we call it a harmonic oscillator. And even better, we right away know what that steady rate is. What we're saying is, as long for anything for all time now, I can't emphasize this enough. and this goes into PChem in a big way for real, and instrumental, as long, like people have come back to me and told me, like, it's one thing that does help to have this in mind in those classes. If you know that something is described by this differential equation here, whatever the z is, if it fits, if it can be described that way, and don't be intimidated again by the omega squared, it just means some constant, then you automatically know that the solution is this. You automatically know that the value of z is oscillating harmonically at a steady rate in time. And furthermore, you know that that steady rate is just the square root of whatever we saw here, which is the only reason we call that thing omega squared in the first place. Please understand, it's Monday morning quarterback. It's hindsight. Like, we could have called that constant anything. We could call it C, we could call it B, we could call it omega. But we call it omega squared because we find out that whatever it is, it's just some number, but the square root of it will be the rate at which this system, whatever system it is, this variable oscillates. Hence, to finish, like, so that in theory, everything I'm saying now, is I meant to clarify or expand or review what in theory we finished already Monday, like finding two. Like, I'm not actually claiming this is new information. I'm just trying to put it together. But then to lastly put it together, remember where it ended on Monday here. Like, so back to this page. I know this is a mess, but like if omega squared is the constant of proportionality in the differential equation, then we have an oscillator whose rate of oscillation will be the square root of that constant. Omega is the rate of oscillation, but it's the angular frequency. It's the rate of oscillation that's most directly easily seen from the math. It's measured in radians per second, right? And so omega squared is measured in radians squared per second. These are direct questions in homework 3. You'll just be asked directly. They're not tricks. If you get what I'm saying now, you'll totally get homework 3. So omega is just cycling rate, but it's measured in radians. So you just have to always remember, oh yeah, there's about 6 radians per cycle. There's 2 pi radians per cycle. So if I take the cycling rate, the angular frequency, I'm just reviewing again, and then we're going to move on, but I'm just reviewing what I think we have so far here. If you have a differential equation that describes something, then you've got an oscillator. I mean, if you've got this differential equation, then it's a harmonic oscillator. It'll oscillate at a steady frequency, omega, which is the square root of the differential equation constant. But then omega is measured in radians per second. If you want to be able to relate to it better as a scientist, as an experimentalist, as like someone in, then you realize that that there's 2 pi radians per every cycle. So if you divide your omega by 2 pi, what you'll get is cycles per second. And we call that measurement standard frequency, and that unit of measurement hertz, right? So omega is angular frequency. It comes directly out of the math. It's how many cycle sixths you're doing per second, technically. So if you divide that by 6, you'll get how many cycles you're doing per second, and that's called standard frequency or hertz. And then if you flip that number, you get how many seconds there are per cycle. In other words, the period of time for one cycle. And that's the easiest number to relate to in the lab and in measurement and in our minds usually. So period is the concrete thing. Omega is the mathematical thing. I mean, and they're interested, and so the point is, the minute someone writes down that differential equation, then our cosine solution immediately tells us, then we immediately know we've got an oscillator going at this angular frequency, which means this standard frequency, which means this period. That's the knowledge we now believe we have. But anytime we walk into nature and we stumble on that differential equation, we now have a tool, basically all this work for a month, and it is a lot of work, let me say again, and I know it feels like in a way you're never going anywhere with this stuff. Anyway, what we now have as physicists is a mathematical toolkit that says, if we happen to stumble on that differential equation again, we know right away we got an oscillator on our hands, and we know all these facts, these characteristics about the oscillator. And the truth is, oscillators are like a fundamental ingredient of nature, like tons of things are built from. It could be a mass on a spring, or it could be an atom with atomic bonds. It's called an atomic oscillator. And everything is built from, especially in PChem. Okay, so now we have oscillators. So now I'm almost afraid to do this, but I'm just gonna move now to homework 2, to the math and start going over it. Okay, and the first one so math methods 2. I guess for 1 second I'll share this screen. I guess. Is it just gonna be for? Oh, no, that was a bad idea. Whoa, sorry. I don't even know where. No, I take that back. I don't even know. Whoa, I don't even know what this. I'm sorry. Hold on. Stop the share. Stop the share. Um, well, all right. Okay, I'm gonna not do that. Pardon me for a second. I'm just so we're going to math. We're going to homework 2, math methods. Um, okay, here we go. All right, so this is not the questions. This is the answer. Like, this is the first one. So math methods, homework 2, problem 1A1. And this, I probably should have put a diagram here, but this is more or less what I would like people's homework to look like. Like you see, I'm trying to make the questions clear without recopying everything, but sort of trying to make the questions clear and trying to put the answers. And I'm not going to race through all of this. Like but I think this first one, I'm doing a little fast here. So I'm going to turn it to you guys in a minute, but this is the first one, just as a warm up or whatever, to get the model. Like it's giving, you see, it's giving me a conjecture for an equation of motion. Like just imagine that we are conjecturing or guessing or considering x equals a cosine omega t, right? It's just now casually asking, well, what would be the first time derivative of that? What's the derivative of x with respect to t? And I did chain rule and trigonometric derivative. And so I get this. Okay, that's my first. And I know we've all done this before, I think, but so I take the first derivative. Then I take the second derivative. Again, chain rule, again, trig. I do that. Then, all right, so I'm looking at, then in B, it asks me now, and this is the key question always, and sometimes we do this forward and sometimes we do this back, but it says, okay, given what you just like found by taking 2 derivatives, is your conjecture, what it's asking in B is our conjectured position function, our conjectured function for x with respect to t, does it solve? Is it a solution to? Does it match? Is it consistent with? And I didn't write it down, but it's asking. Sorry, I'll just add the page. What the question is asking in B is asking, does this solve this and it's asking in a mathy way now. Like you and I happen to know this thing that I just wrote, this diff EQ, this is a physics thing, right? But the math is just right now asking, it doesn't care about physics or know about physics, it's just asking, is this a correct version of X given this version of the second time derivative of X? And what I'm going to say, the answer is yes. Like, so the answer to it is yes, but why? Because we just took 2 derivatives and we found, and again, I do want to make this as clear. There's like a step in here that's always really, it's easier to see when I do it, and it's easy to forget for you to do it unless you practice this a lot. Like I'm saying, we just learned on the back page, we saw that d2x, like by taking 2 derivatives, what we technically got was this. Right, like this is what this line right here says. Okay, you take 2 derivatives, and I got this gobbledygook. Okay, and a lot of people in the class can do that, but then often, if I then ask, so therefore what? Like, what does that prove? It's hard to see right away if you just see this gobbledygook. Like, yeah, what does that prove? I don't know what that proves. Like, yes or no. Well, the thing that you always have to train yourself to remember to see is like right here. This part is exactly what we were guessing to be equal to x. Like the whole thing that we're testing is, does it work to say that x is equal to this whole thing? So that is what we said was x. So therefore, apparently, so like if this whole thing here is x, then the answer is yes. Like, oh, the second derivative with respect to time of x does equal negative times a crazy constant times x itself. Like that's what we just showed. It once you see it, it seems so obvious, and that you can't even imagine like what you just did, which is why we then go to the other examples where we show no, some things don't work. Like this doesn't always work. Some things solve the differential equation, and some things don't. We'll see that. But an example of working is this right here, when in fact, so what we're saying in English is we're looking for a function which, when you take the time derivative of the time derivative of it, you get back itself times a constant times a negative. That's what we're looking for. And this thing says yes, but you can't see it. Oh, sorry. You can't, sorry, that's not what I meant to do either. You can't see whether it's yes or no unless you do that last step of substituting x back for whatever you got. So sorry, wait. So we were right here. Sorry. So I think we're here, yeah. Okay, so that's A. Again, if you've already done it, hopefully you got it right and you get it. If you haven't done it, you're welcome to, but does everybody get that? Like, I want to pause for a second because I've just been yammering and yammering. Whether it's interesting or not, is it clear what I just did in A? Can I just pause for a second and either get, in fact, change my view to gallery? So I'm just, could anybody give me are we, okay, thank you. I'll take it. Thank you, Ardell. Okay, bored but clear, fine. So now we go on to B. Was it? Or that was B. I'm sorry. Now we're going to C. Right? Yeah, we did all that. Sorry. Okay. Oh, now I'm jumping the gun here. Sorry, but C, I guess I don't mean to jump the gun. I meant to let you guys do it or whatever. But to cut to the chase, yeah, we're going to find in C now. C is intentionally designed as more practice, but it's intentionally designed to show us that just even understanding cosines and everything, like this is all about cosines for a reason. Why do cosines keep coming up mathematically? Because the derivative of cosine is negative sine, and the derivative of negative sine is negative cosine. So cosine is exactly that kind of thing that when you differentiate it twice, you get back to itself with a negative sign. I'm not saying it's the only thing, but it is a thing that does that. So we're playing with these cosines, but now we're trying to show ourselves, well, we have to play carefully. Like just because we write some cosine thing down doesn't mean it works. So like, I guess to talk us through this, in C, we were given, it's also now assumed in C that we get the model of how to do this. So it's like cutting to, it's just asking right away and assuming we'll follow the procedure. If we're given T2x dt squared equals negative 3x, like what they asked in C is, does x equal a cosine 5t work? Now, it's again, this is not meant to be a trick question. This is meant to be a point, like just like hopefully it's not hard, but it just shows what's going on, which is x equal, like put it this way, x equals a cosine 5t is a very reasonable thing to write down. Like that is the description of some oscillator. That is an oscillator. And this differential equation I'm looking at is an oscillator. So it certainly seems like, you know, and I paid attention, I put in constants and stuff. But if we're careful and we check, so it's always about checking by taking derivatives. If I take that expression, x equals a cosine 5t, and I take one derivative, I get negative 5a sine 5t. Then I take another derivative. Now I get negative 25a cosine 5t. So cool. Once again, cosine comes back, good news. The negative comes back, good news. I do again what I did in the last page. Like I say, oh yes, a cosine 5t. You're all a bunch of gobbledygook, but I recognize you gobbledygook from 5 lines ago. Like you're the thing that I'm testing out as x, you gobbledygook, x, you. Like, so this whole thing is x, a cosine 5t. So note that key step that I'm saying, it's secretly, it's the step people always forget on exams. The step of substituting x back in, like it's impossible to see what's going on unless you do that. And no one can tell you to do that. Like you have to remember. But anyway, if I do that, if I substitute x for a cosine 5t, notice it works. Like I'm not wrong. Like that is x. But what I find is, oh, d2x dt squared here apparently equals negative 25x. And that's nice. That is a differential equation. That is an oscillator, only it just isn't the oscillator I was being asked about. 25 doesn't equal 3. So like it's not meant to upset anybody. It's meant to say like, so here's a counterexample. Here's an example of something, of a cosine expression that does not solve our differential equation. Like this would be an improper description. In other words, what I'm really saying is if this is physics, which like it's supposed to be, if I somehow came out of a lab knowing that this differential equation, the one that I just like boxed in black, what I really know is that I've got an oscillator that's going back and forth with an angular frequency of square root of 3 radians per second, like 1.7 radians per second. That's what that thing is saying. Only this thing down here, this thing is looking at something that's oscillating 5 radians per second. That's the difference. They both have the same amplitude, but one's going like and one's going, if that makes any, okay. So the answer to that one to C is no, does not work, is not a solution yet. Nugatory. Okay. That's C. D, if I recall correctly. All right, I'm going to keep flying for a little bit. Like I will pause and take a break, but I think D is just a little more practice of the same thing. It's not like terribly interesting. So I'll just get it off my chest. D, they give you another X expression. They ask you to differentiate it twice, right? This time they give you A. D, as someone else in the other class said, D is basically now the steps that hopefully you knew to do in your mind in order to get an answer for C. D is kind of like justifying or proving that you're right with your answer in C. Presumably you kind of already did this, but so D is dragging out saying, look, let's check the derivative of A cosine 5t. You get negative 5A sine. Then you do it again, you get negative 25A cosine. So that's it. That's what D is asking for. Those are the answers. And again, if you're following this, you can write it down for your homework as long as you're actually following. If you're not, please tell me. Then A, all that A is doing is now is repeating the same thing, but now it's kind of like we were hoping we're getting used to in A and B, we're thinking mathy. Now E is reminding us, hey, yo, by the way, remember this came from physics in the first place. As long as you got a mass on a spring, what we proved in finding one is that omega, that constant, it might actually come from the lab. It might be the square root of K over M. This all still works. I mean, that's where it came from in the first place. And by the way, I've never actually explicitly said this, but you may want to check yourself. Square root of K over M has the same units of omega. It has to, otherwise this doesn't work. Just remember that radians themselves are just placeholders. Anyway, you can check, it does. But okay, so I take a derivative here, just like before, it's just the same procedure. And I take another derivative here. I'm on the next page, I'm on 4, please stop me if you want. And I get, and then it doesn't even ask me, but it should have asked me, like, so does that satisfy? Like, so does this satisfy d2x dt squared equals negative omega squared x? And yes, it does, as long as square root of K over M is equal to omega, if that makes sense. I mean, that's but believe me, I will, again, now this next one gets a little bit more interesting. Now we get to something in this next one. So I'm going to slow down a little bit. You can still go back and ask me of anything before, if anybody's catching up, or you can ask me to turn back the page or whatever. But I think I'm now up to F. I think this is F. Yeah. And I know the Roman numerals become wackadoo for no good reason. I don't know why the Roman numeral system did what it did, but I'm just keeping it. So we're looking at F now. F, what we're given is once again a cosine expression. Once again, a cosine expression that begins with an amplitude, but now someone went ahead and stuck something in the parentheses behind our back. Definitely that was an aggressive gesture. It was a microaggression, actually. Hold on. There's literally now a thing, an extra number sitting in our parenthesis. Now, before we go any further, I want to say, and that's meant to be, again, it's not meant to trick us. It's meant to advance this one step further and see what's going on for a reason. I will say before we get any further that number 3.5 that I'm sticking there, okay, first of all, it's just meant to be a random number. There's nothing special about 3.5. Don't overthink it. It's just meant to be like any old number. But I do want to highlight that there always has been a number there, even when we didn't realize it. What's interesting about 3.5 is not that it's any particular number, but just that it doesn't equal 0. I'm saying that in a way, we could have always written a cosine omega t plus something, but we were secretly always writing plus 0. We were assuming that there was nothing being added. Now we're about to find out, well, what happens if we add some non-zero value there? Okay, so we're going to find out. So I should have asked you guys this, but it's already written down, so I'm a bad person. More on that, details on 11. But since it's already written down, I'm not going to pretend. If I take the first derivative of this new, so again, I'm trying a new expression. It's a conjecture. It's a guess. It could be motivated by anything, but it's basically me saying, all right, cosine solutions work. Can I make the cosines like a little bit more complicated? Like, you know, what will happen? I'm just playing. So if I take the first derivative, I get negative a omega sine omega t plus 3.5. Now you really, this is where, if you haven't done the homework yet, totally fine. But before I go on, you may want to jot down on a piece of paper. Like, I encourage everybody, please take this derivative yourself. Don't believe me. I'm not saying I'm lying, but don't take my word for it, because you want to try it yourself, because you want to see that you come to the same conclusion. Like, this derivative is, again, chain rule and trigonometric. But I mean, just to be as clear as I can, but like, we are about to see something here. Whoops, sorry. So like, I am saying that 3.5 stays in the parentheses, but it does not come out and get carried for the ride. It does not get carried along with the omega. Like, to be as more specific, I'm saying the way we get this derivative is we first say, okay, derivative of cosine is negative sine, fine. But then we have to do the derivative of what's inside the parentheses, right? Because of chain rule, which we've always been doing. We've always been taking the derivative of what's inside the parentheses, and then multiplying by the whole thing. That's why we've been multiplying our whole answers by omega, and then by omega again when we take a second derivative, right? So I'm still doing that here, but at the risk of condescending to anybody, or at the risk of boring anybody, just remember that, like, if we take the derivative of this whole inside, we're taking the derivative with respect to t. Like, t is our independent variable. So think of this whole thing as like constant times t plus constant. It's like mx plus b, where you're taking dy dx. Like, in fact, like literally exactly that's what this is. This is like taking the dy dx of an mx plus b. And I'm just saying here, unless anybody like questions in the chat, I'm saying the derivative is just that m, right? Like, the derivative of omega t is omega, plus the derivative of 3.5 is 0. Important. Just like mx plus b, the derivative of the mx is m, the derivative of the b is 0. That's what's happening here. So when we take one derivative, omega comes out. We multiply the whole thing by omega, but we don't multiply by like omega times 3.5 or anything like that. Yet notice the 3.5 does stay in the parentheses, because like that is the function in the, so the 3.5 is doing something. It's there. We're not ignoring it, but it doesn't come out of the, and then when I do the derivative again, same thing. I get negative a omega squared cosine of omega t plus 3.5, right? Like, that's, I'm claiming. And please stop me in the chat, and it can be private. I will not shame you. If you don't get what I just said, there is no shame. But if you know that you don't get it, it's like totally not too late. This would be the time. But okay, but if you do get it, and it's still not too late, going to the next page, still not too late. In the Church of Physics, all are always forgiven. Well, unless the church like is at a college and gives grades. But okay. So wait. Oh, so whether the homework introduced this like new cosine deal with the 3.5 in it. I don't even remember if the homework asked or not. But if you're getting the model of what's going on in the homework so far, the question always is, given some cosine thing, like, is it a solution or not? Specifically, is it a solution to our differential equation for simple harmonic oscillation? Like, we are physicists, we're all concerned about oscillators, which means this differential equation. So I'm asking, I mean, I'm not, you can put something in the chat if you want, but I'm like asking myself, okay, given this expression, then where chain rule applied like in a maybe a surprising way, like, does this thing work? Could I use this to describe a harmonic oscillator? And evidently, well, like if you look down at the bottom here, like, remember this whole thing is what we're calling x, is what we're trying out as x. So since that whole thing got carried through in the two derivatives and nothing funky happened, like, and since the 3.5 didn't come out, it appears that yes, not no, like yes, like apparently this cosine omega t thing that we've been playing with for 2 days, that we've been saying is a solution to, like, for 2 days we've been saying, oh, if we've got this differential equation, then we've got an oscillator that can be described this way, cosine omega t. What we're now saying is, oh, apparently that was true, but apparently it wasn't the only solution. Apparently we'd been assuming a 0 in there, and apparently we could be more expansive than that. We can actually try things that don't have a 0 in them, and mathematically they'll still work. which raises the question, well, then do they have physical meaning? Like, would this be a better way? What does this mean physically? Like if this, like, that's what I'm saying. This is now a more general solution that apparently does the math fine. So like so does this mean that the physics equation that we really want to describe oscillators might in fact be more complicated? And the answer is yes. Yeah, this. Okay, so you copy that. So evidently, so you can call this finding 3 now if you want. I don't know how many findings there are, but we're now pushing. Basically, each finding is more generalizing the finding from before. Like first, we figured out something about a mass on a spring. Like we just wanted to figure out something about a mass on a spring, but then the math exploded in our face. So we go and we do all this math, and we come back. We're like, we got it now. We got the mass on the spring. Thank you, math. But then the math voices are like, oh, I guess now that we understand a mass on a spring, I guess we understand a heck of a lot more because we now understand anything that obeys this math. That's kind of cool. But then in finding 3, we're now saying, oh, and if we're willing to generalize, then actually that math equation that we came up with, the cosine one, we can actually cover even more cases with that if we add a constant. We're now going to say, oh, you know what? Here's a solution. You want a solution? You want a solution? I'll give you a solution. Are you talking? The solution is not just a cosine omega t, as in not just a cosine omega t plus 0, but from now on, x can equal a cosine omega t plus this new Greek letter that I'm introducing a new Greek letter, a new lowercase Greek letter called phi or phi, phi. And pronunciation is up to the user because the spoken language of Greek is not anymore. So no one actually does know how to pronounce this. And anybody who says they do is lying because they're not dead. They might know how to spell it, but they don't know. Anyway, so this letter, this lowercase phi or phi, is now allowed and in fact required in our equation from now on. We're actually advancing now. From now on, when we want to describe an oscillator, we're going to have to say it's an a cosine omega t plus this thing phi, which is some kind, again, I don't know much about it yet. I just know it's a constant, it's a number. I'm allowed to put a number there and it won't change the derivative. And I know it must be measured in radians. It must. Even the math, like if the math cares about units, that phi, whatever it is, it's got to be some number of radians because it's being added to omega t. And you can't add apples to oranges. Well, you can, but then you have fruit salad, like which anyway, like you cannot add feet to pounds, you cannot add meters to kilograms, right? You can only add kilograms to kilograms, like for reals, yo. You can multiply meters by kilograms, but you cannot add a meter to a kilogram and get anything meaningful in science. So, and put another way, you can't take the cosine of anything but like a radian or a degree. So this is in the parentheses, it's being added to omega t. This is some kind of extra bit of radianness, not radians per second, right? Not radians per second. Omega is radians per second because then that gets multiplied by t to make radians. This thing is by itself. Whatever it is, it's just radians. I'm yelling for no reason because I'm excited. And I'm thinking that loud is clear, but I don't know why I think that. So we're now saying that anytime you thought like you were cool with this a cosine omega t business, we're actually saying now, actually, could you expand that a little bit more and call it omega t plus phi, where phi is just any kind of number. Like apparently that will work. Now, what is phi? Like what the heck is it? Wait, yeah. What phi is, it's like a head start or a delay. Actually, let me just add one thing. In fact, you know what? Sorry, it might even be better. It might even be more clear. Like most people write it as phi. The truth is it might even be more clear if you write it like this. It's whatever you want. But it is, what phi is an initial position. It's like a starting position. It's very much like, and there's a whole homework on this anyway, but like, okay, phi naught is kind of like the x naught in x equals 1 f a t squared plus v naught t, which like some people leave in the x naught sometimes and some people don't, because like that x naught, a lot of time, That x naught means initial position, place where object was at time equals 0, right? Like that's what x naught means. And the reason, like a lot of times we don't put it in at all is because a lot of times we set things up so we just say wherever the object was at t equals 0, we just call 0. So a lot of times it drops out. That's kind of like what's happening here. Phi naught is like where the object starts. It's like, or if phi naught is negative, it's where the object, it's a head start or it's a delay, but it's measured in radians. Okay, so this thing, this phi, is called the phase constant, and it's telling us where initially the object starts relative to phase, relative to cycles. Again, being measured in radians. So like it always comes back to there's 2 pi radians per cycle. Like that's the hook of all of this, like 2 pi radians per cycle. So what we're used to, like, and all this is, again, I'm trying to explain what the purpose of that exercise in math methods are. It's like introducing that number because we're going to have to deal with it in physics. Like, go back to thing on a spring, homework 1. Our mass started at an initial position at an x naught that happened to be 15 centimeters in that example, right? What did that mean? When we say we started it at 15 centimeters, it meant 2 things, really. It meant that that's when we started our stopwatch. Like when we say the object started there, like we don't mean it was born there. Like the object has been other places. Like what do we mean started there? We mean the experiment started when the object was there, which means realistically, as you saw in lab 1 and lab 2, the truth of the matter is probably, if we wanted to take good data from this oscillator, probably the thing didn't start there. It was probably going for a while, and then we started our stopwatch right when the thing was there at 15 centimeters, right? And we did that. Why did we start our stopwatch right there at 15? Because we had already come to notice after a pattern, after a while, that 15 was the turnaround place. Like we noticed that 15 was as far as it ever got, the amplitude position. We noticed right then the object was coming to a halt, was stopping temporarily, and then starting to go in the other direction, right? So we started our timer at a place of V equals 0. Like, because it makes a lot of sense to, because it's natural to, because it's easy to. And then from there on, we counted cycles. Like a cycle is like there and back, from positive 15 to negative 15, back to positive 15. That's a cycle, right? That's what we were doing. And in effect, then we were measuring cycle, we were timing from the beginning of cycles. But if you can imagine what we could have done, we could have started our stopwatch when the object was midway through its cycle. Like instead of starting our stopwatch right when it was at the 15 positive centimeter amplitude position, we could have waited till it already went halfway through its cycle and went all the way to the other side. And we start our stopwatch and then it comes back. Like we could have done that. And if we had done that, we would say, in effect, that this object started with a head start or a delay of a half cycle. Like already it was halfway into its cycle when we started the watch, i.e. it was pi radians into its cycle because there's 2 pi radians in every cycle, right? Or if we had started our timing when the thing was at equilibrium position, then we could say, oh, pi over 2 radians have already gone by, a quarter of a cycle. Okay, so that's what this term means physically. It's the head start with respect to cycles that you get. And I'll say one more sentence, and I really will shut up for like a second. This phi thing, which up until now we've been treating as 0, and now we're discovering, oh man, phi could be non-zero, and still all of this works. So it allows us to be able to track like where something starts. Just like in physics 1, just like with x naught, sure, whenever possible, we're going to make anything as convenient as we can for ourselves. So whenever possible, we're just going to start our watch like at the amplitude position. Or quite frankly, if we don't, for some reason, if we start our watch somewhere else, we'll still call that the beginning of the cycle. Whenever we can, we're going to just call wherever we start the beginning, and we're going to make this term 0, just like we did with x naught. Whenever we can, we just start objects at 0. But the reason we have to know about this term, just as foreshadow or whatever, the reason we're not always going to be able to get away with that. When we can, we'll start wherever we start measuring cycles, we'll just call that 0. But the one circumstance where we won't be able to get away with that, just so you know, and it's about to come up, is whenever we have more than one oscillator. I should have asked you all this, but I'm on a roll now, I guess, if you call it a roll. Whenever you have, the reason we would ever use x naught in x equals 1/2 at squared, blah, blah, you always make x naught 0 when you can. But the one you can't is if you have more than one object and they're starting at different places. Like if you have, like in the big old duck problem from last semester, for those of you who remember, it's anything, like if you have two objects and they're starting at different places, then you make where one of them is at the beginning 0, sure. But then the other one, if it's starting in a different place, wherever it's starting, you can't call 0 because you already called the other thing 0. So when there's more than one object, like you have to keep track of head starts or delays. When there's more than one oscillator, we're going to have to keep track of head starts and delays. And we are very shortly going to have situations with multiple collections of oscillators. They're called waves. So that's why this term is going to be important. It's the term that's going to allow us to handle multiple oscillators, which are ultimately called waves. And so that's where this is going. So I'm going to go back to the math sheet now. I mean, the homework sheet, to do the next exercise, but I'm going to literally pause for like, we have like 15 minutes. Yeah, I'm going to pause for like for like 2 minutes. Please everybody take your time, like look at your notes. I'm going back, I'm at where I think I am in the world right now. I mean, in the world of this class, where I think I am, is I think we just did part F. I think I've said all that I want to say about F and like why it's significant, what the purpose is. So momentarily I would be going on to, I guess, G, which is, oh, sorry, that was F, G. Tell me, I think this is the next thing. Maybe I skipped something. Well, I'm sorry. I'm going to go on to the next one in a second, but I want everybody to pause because I've been yammering so much and because everybody's at different places. Please, like, just stare at your notes for a second or stare at your homework and see if what I'm saying makes sense. Also, any of you, more and more, any of you, whenever you're in doubt or if you're falling behind in homework or anything, you're welcome. I'll open up a portal for this. I'd love to see glimpses of people's notes. I mean, no, I don't want to spy on anybody's notes, but there are those of you who take really good notes, but then don't know what to, but then like are worried about other stuff, but you're like responsible and you're attentive, but you're worried about stuff or you're confused or whatever. If you ever just take a scan of like some of your notes and send them to me in any portal, or I'll open up a new one, first of all, it would help you show me that you're doing, like, if you're worried about what I know, show me your notes. And a lot of times people's notes really help me see what of mine is getting across and what not. So any of you at any time is welcome. That's another example of something you can do just to show me, like, but no one's obligated. But anyway, having said all that, I'm going to pause for a second so you can really see if there's any questions with anything I've just said. And again, if you think you have a question, you might think I have a question, but it's because I wasn't paying attention 2 months ago or 2 years ago. Don't worry about that. Put it in private chat if you're worried. And I'll tell you, if your question ends up being showing that you just don't even know how to add fractions, okay, maybe we do have to deal privately, but I still won't shame you for that. Like, my wife can't add fractions. I mean, honestly, like, I mean, that's just the way it is. So look at your stuff, and believe me, she can do a lot that I can't do. That's not obvious, but look at look at your notes for a second, and I'm also going to recalibrate for a second. I do want to get through one more example today, but only one more. So, I mean, one more exercise. Oh, sorry, that was F and G. Oh, so I'm sorry. So everything we just did was F and G. I'm about to go on to H, and H and I will be the last thing we do today. We will not do J. J is very interesting. That's the next one, but I'm about to do H and I. But I do want, also, I want to say, well, I'll be quiet again for another, but like there still are a ton of you that do want to turn this in, like not a ton, like about half of you have turned it in. A lot of people have gotten it back, but there are about half of you that do want to turn this in. So I really, again, it's not late, but maybe really look at it now and see if you feel like you can do this stuff now that we're talking about it. Because hopefully it is getting clearer and the rest of the stuff doesn't get easier. All right, but if that, so I'm going to start setting up H. Oh, wait, sorry. Okay, so if there's really no question, wait, okay, if we're really all okay, I'm going on to do H and I here and J. I mean, I'm going on to do H. Notice I'm still believing in the chain rule, like the chain rule is still true. And that's note number one. You might not recognize it. I certainly didn't when I first saw it this way, but note number one here, it's just saying the chain rule is true. Like that note number one is just the chain rule. And you may or may not think of the chain rule that way, but to me, it blew my mind when I first saw that that's the chain rule. Like it made so much sense to me. So, like suddenly I was like, oh, this crap makes sense. Like, right, because the chain rule is saying just like the chain rule is if Z is some function of Y, and then Y in turn is some function of X, right? Like that's what the chain. So I mean, Z again just has some general variable, right? But just side note math reminding you or getting us up to speed, like the whole thing of the chain rule is what to do with functions of functions, right? Composite functions, such as cosine of omega times t, right? Like that's a function of a function. So what the chain rule really says is, yeah, if Z is a function of Y and Y is a function of X, well, then the derivative of Z with respect to X, like the derivative of the outer function with respect to the inner thing, is really the outer with respect to the inner times the inner with respect to the outer, and kind of like duh because these are because duh. Do you see? I mean, just a notational way of writing chain rule, but it might make some sense out of it for some of you. So the chain rule says do the outer times the inner, and it's a chain because you can do that recursively forever, no matter how complicated the function is. All right, so we're still using that. But now also reminder from math class. Now I'm going to say also in general, maybe I should have used Z's again here, but just any general Y or X. If your function is Y equals e to the X, where e is that fancy number, I should say, not that it actually matters, but where e is is a certain constant number that has incredible intrigue and power and all this, but it is just a number. Like it is transcendental. Like it's like pi, it's infinite, non-repeating. It's like worse than irrational or better than irrational. If you like, it's technically a transcendental number. It's 2.71 bleep, blop, bleep, blop, bleep, blop forever. Okay. But that doesn't matter for the moment. Like all that matters is it's that number. But this number, apparently, when you raise it to the power of x, right? Not x raised to it, but when it is raised to the power of x, which is now a whole new concept, like for us, like never happened in physics yet. I mean, not in our class, but apparently for math, when e is raised to the power x, the derivative of that, the rate of change of that is that itself, right? Like if y equals e to the x, then dy dx is also exactly, precisely e to the x. Now that's from math class. I am expecting you've seen it before. I'm expecting like this rings a bell that you're like, oh yeah, derivative of ex equals ex. I'm also expecting anybody who's saying that they get that is lying to themselves or me or saying, because like maybe not anybody, but to get why that's true, like that's a big thing. And I am not claiming, and you don't, and I would like to talk about it with all of y'all, but like let's not kid ourselves. It wouldn't be fair for me to expect you to understand why that's true, even from a math class, even if you aced it, because I don't know how much time they have to go into that. Suffice to say, for the moment, in my head, for the best thing that so you're okay. It's okay to sort of take this on faith a little bit for the moment, or to borrow it from your faith memories from math class. I will say that one way to make sense out of it right now is actually that's the definition of e to the x in a way. Like e to the x is that one and only function which is self-differentiable. Like in a way, e to the x is just the name for the concept that someone wondering, is there a function in the world? Like remember cosine we like, because cosine was like you take the derivative of it, you get something sort of similar, negative sine. Then you take the derivative of that and you get negative cosine. Like there's a way to take derivatives. And in fact, if you really think it through, if you do it again, then you get sine, right? If you take it again, the third derivative, I've never said this before, but we are going somewhere with this in the sheet. If you take negative cosine again, you'll get now negative sine. No, sorry, you'll get sine. And then you take the derivative of that and you'll get cosine. So there's a way to get back to the original by taking enough derivatives. So one might ask themselves, are there any functions that you could just do that right away? And the answer is the one and only one function that you can do that. We call it e to the x. Whatever else it does, we'll try to uncover here in class, but like it's just the name for the function that is self-differentiable. So, but I think you do know that from math. Like the derivative of e to the x is e to the x. But then, therefore, with that, and this is where I know we have 2 minutes, crap. But with that and with chain rule, just to do this example, all right, I just wrote all that. Well, then, right here is the answer. Like if I take the first derivative, then by chain rule, I bring down the negative omega, right? Like, sorry, the first derivative, I get e to the negative omega t. Like that's the first, but that's the derivative of the outer function. But then I have to multiply that by the derivative of the inner function. So I have to multiply it all by negative omega. So there's my first derivative. Now I take a second derivative. The same thing's going to happen again. I do again e to the negative omega t, but times negative omega. So now the negative omega comes out again. So I get omega squared like before, but now I have a negative times a negative. So I get a positive. So, and here's where we're going to end. I know it's like 419, but here's the point. Like if we're very careful, we see that this one comes close, but no cigar. If we suddenly try an exponential function and see if it satisfies our differential equation, we find that it has the right flavor. And this is why we tried it. We tried it because we're like, wait, don't we want things that like when you differentiate them, you get back to themselves? Well, yeah, that's what happens with E, but it doesn't obey the sine thing the way that the cosine does. Like it blows it on the sines. We don't get our original harmonic oscillator. We get like, if you turn it to the side here, I don't know if that, no, you can't. Oh, anyway, if you look at the side, what we get is that the second derivative equals positive omega squared times x. That is some kind of differential equation, but it's not ours. It's not Hooke's law. There's no negative sign there. So the answer is this doesn't work. But the reason we brought up, it's not a failed mission. It's like science experimentation. We tried E. I asked you to try E for a reason, because E had that differentiating quality. And it almost worked except for the negative sign, which suggests that maybe if we play enough with E, or we do something with E, we can get E to also describe our oscillators the way cosines do. And that's like where it goes next. But that's it. That's okay. That's it. But it's exactly 420. So I'm ready to say I will hang here until everybody's gone. So any questions at all, I'm happy to answer them right now. You can hang it and ask quickly. But other than that, I'll say goodbye. And each and every one of you, when you go, if you could just say goodbye, even though I won't be able to say it after, but just like it's goodbye time, unless you have a question, I'm here. But like goodbye or thank you, or I hope you heard any of that. Or
Bye.
okay, bye. Thank you. Okay, bye. Bye. Peace, so to speak. Thank you. Okay. Thank you. Bye. Bye. Thank you. I think, okay, thank you, Melissa.
Have a good weekend.
Thank you. Yeah. Oh, right. Yes. Have a good weekend. Thank you. You too. Thank you. Oh, and bye. Thank you. Bye. Also, okay. Thank you. Bye. Bye. Thank you. Bye. Bye. Thank you. Bye. Bye. Thank you. Bye, Brian. Leslie. Bye, Crystal. Bye, Amanda. Bye. Thank you. Bye. Bye. Awesome. Bye. I like the bye. That's cool. Bye. Okay. Bye, Kaylee. Thank you. That's good. And Tania, thank you. Thank you very much. I totally appreciate it. And then Tania, are you good? You good? Tania, you're good? Bye.